Hello everyone and welcome to lesson 2.2 Forces, part 1 of 2. This is the slide that I always like to begin on because it has the data booklet reference and it tells us where in the data booklet we can find the formulas and which formulas they are. So if you can grab your data booklets, if you haven't done so already, just pause the video and take it. So we want to go to the page with core equations, and right now we're in box 2.2. So far we have looked at topic 1.3, so this should make sense to you. 2.1, we've got all those formulas. These two will keep coming up throughout the rest of the course. And now we're in box 2.2. So we've got 3 formulas, which we're going to cover throughout this video and the next video. Yeah, let's go back to the slides. Okay. So we're just going to pass through some of this stuff because it's IB. Okay. Now we have talked about forces quite a bit, but we haven't really defined what it is. So a force is defined as a push or pull, and the unit of measurement is called the Newton, and it's symbolized by capital N. I don't know how many of you watched Looney Tunes or ever saw the cartoons with Wile E. Coyote and the Roadrunner. This might be before your time, but they were pretty funny cartoons, and usually for Wile E. Coyote, he was trying to find some way to destroy the Roadrunner, and in turn ended up always destroying himself. So in this cartoon, he only notices gravity acting on him after he realizes he's off the cliff. Of course, gravity doesn't work like that. The second you run off the cliff, gravity starts acting on you and you fall. It doesn't start working once you realize that it exists, right? So gravity we have learned through another name, and that is the weight. So now we know that if you stand on a scale, that is not actually measuring your weight. That's measuring something called the normal force. Weight is the force of gravity acting on you. Okay, now vectors we know are quantities that have magnitude and direction, and because forces have magnitude and direction, therefore they are vectors. Now with weight, because weight is the force of gravity, gravity is an attractive force, and it is the force that attracts any two objects that have mass towards each other. So let's consider you and the Earth. You are attracted to the Earth, but the Earth is also attracted to you. The reason why when you jump off, let's say a flight of 3 sets of stairs or 4 sets of stairs onto the sidewalk, if you jump off some stairs or you jump off some kind of a height, the reason you fall to the ground and the ground doesn't come up towards you is because the Earth is so much more massive than you are, so much more. And even saying so much more is quite an understatement. The Earth is exceptionally massive. But in reality, just as you are moving down towards the Earth is moving very, very, very slightly upward towards you. But the effect is almost not noticeable. In fact, it's not noticeable to us because it is so massive. Now, the direction of the weight, we always draw it as going straight down towards the center of the Earth, hence towards the center of mass. So if you have a weight of 90 newtons, or abbreviated as 90 with N, your weight can be expressed as a vector. So you have your magnitude of 90 newtons, and of course the magnitude has to come with a unit, and then there's your direction, down. Okay, weight is given by the formula W is equal to mg. M is mass, measured in kilograms. G is the acceleration due to gravity. Now, while in the slides it does say 10 just for simplicity, we are going to be using the value in the data booklet, which is 9.81. Okay. So we'll come back to that formula. The first thing we want to go over is Newton's first law. So in this video, we're going to be going over Newton's first law, and the next video we'll go over his second and third laws. So the first law surrounded studies provided by Galileo and Aristotle. So Aristotle said the natural state of motion of all objects but the heavenly ones, hence those in space, is one of rest. But a child knows that if you stop pushing a wagon, the wagon eventually comes to a stop. So naturally, this made sense at the time. The natural state of motion is one at rest. If you kick a soccer ball, it eventually comes to a stop as well. So for many people at the time, it made sense. But there's another reason why it comes to rest. And we're going to show that not only the first blue statement, but the second blue statement, they're both false. The second observation they made was, in order for a body to be in motion, there must be a force acting on it. So the idea that because a force was only initially applied, once the child stopped applying a force to the wagon, it would come to a stop. Okay, so now we know that actually both of these observations are false. Okay. So this is what Galileo thought. So on the earlier slide, that was Aristotle. Now we're looking at Galileo. And so if you give a cart a push on a smooth level surface, it will eventually stop. And sure enough, if you do that, that's exactly what you're going to observe. So it made sense at the time, like I said earlier. So what could he do then to increase the distance it rolls without pushing it harder or changing the slope? Well, he knew that there was some resistance between the tires or the wheels and the ground. So if he reduced the friction, he reduced that resistance force, then this thing should go further. So if you, for example, oil the wheels, if you grease the wheels, well, you're going to reduce the friction between the wheels and the surface. So given the same push over the same level surface, it will travel much further. But again, it's going to come to a stop because there's still friction. And he theorized, so Galileo theorized, well, if I take out friction completely, the cart should theoretically move forever at that same speed. And this was actually the correct analysis of the situation. So Aristotle had some good ideas, but unfortunately they were incorrect. Galileo's ideas, on the other hand, were correct. And Galileo therefore coined the term inertia. Inertia is the tendency of an object to stay in its current state of motion. So it's said another way, an object wants to keep doing what it's doing unless acted upon by an external force. Okay, so theoretically, this thing should go on forever in the presence of no friction. Okay. Now here comes Newton. So Newton went ahead and used Galileo's idea of inertia, and he also combined it with some of his own ideas to come up with what we now know as Newton's first law. So he used Galileo's concept of inertia, and his first law now says that if you have an object that's moving either at constant velocity or at zero velocity, in other words, it's not moving at all, then it will maintain that state of motion or lack thereof as long as there is no net force acting on it. Now, no net force, that means there's no total force acting on them. You could have an object and apply a force. So let's say you have a box in the middle of a room sitting on the floor. If you have one person pushing on it from one side with a force of 15 newtons, and you have another person pushing at the exact opposite side in the exact opposite direction, also with a force of 15 newtons, well, there are still forces acting on the object, but they balance. And so there's no net force. So that object's going to stay at rest. But if there is an unbalanced force, in other words, if there is a net force, then the object will not maintain its current state of motion. It will change. And so this is what exactly, this is how his first law was stated. Every body continues in its state of rest, which is a velocity of zero, or of uniform motion in a straight line, which is a constant velocity, unless it is compelled to change that state by forces impressed thereon. And the forces, we're talking here about the sum of the forces. So sum of the forces or net force, those two words mean the same thing. So if you want to represent this using symbols, Newton's first law is, if the sum of the forces is equal to zero, in other words, the forces are balanced, if there are any, or there might not be any forces, then the velocity is constant. So the sum of the forces equaling zero is what we call the condition for translational equilibrium. You've seen this word before, equilibrium. It means balance. Things are balanced. And in this case, we're looking at a balance of forces. Translational means the object is in motion. All right. Now, think about the following example. Imagine you have a water balloon that is cut really, really rapidly with a knife. I mean, it would be really cool to actually watch this in person, but just go with this for a second. When you cut the water balloon for just a split second, that water is going to maintain its shape before it collapses to the ground. Now, it's going to be a very, very tiny fraction of a second, which is why if you were to capture this with a camera, you would need a very, very good camera to capture it. So it would look something like this. So for a moment, the water does stay the way it is, but since there's no more force keeping it in its shape, it has to change its tendency of motion. Don't ever try this at home, by the way. All right, let's keep going. All right. Calculate the weight of a 25 kilogram object. So this is just us getting used to the formula W is equal to mg. There is something I want to point out. So we're going to go to the page here, but at the same time, I want to show you something important. So if you look at the formula booklet, and after all, we did start with the slide of the data booklet reference, notice that there is no formula here, W is equal to mg, and it's not in any of the other boxes either. Okay. In fact, that formula does not show up anywhere in your data booklet. But it is a very, very important formula. Now, it was not excluded on purpose, just as this formula was not excluded from the 2.1 section on purpose. So in lesson 2.1, we learned these four kinematics formulas. And in addition to that, we learned that velocity is equal to displacement over time. Actually, it's a bit hard to see that. So let me see if I can hold it up to the, camera. There we go. Velocity is displacement over time, or displacement equals velocity times time. We can only use these equations when dealing with projectile motion in the x direction, because in the x direction, acceleration is 0. And well, of course, even if you are not dealing with projectile motion, if an object is just moving across the ground or walking or rolling, you can use these equations as long as acceleration is 0. Now, even though these equations were not written in the box, and in fact, these are the same equation, they're just rearranged. So just because this equation is not written in the box doesn't mean it's not here. In fact, if you look at the second equation, s equals ut plus 1/2 at squared, it's there. If your acceleration is 0, then this whole second piece, the piece after the sum, the plus sign, disappears. And you have s is equal to u times t. Now, if you have no acceleration, then that means there's no difference between your initial and final velocities. They are the same. So you can call it u, you can call it v. So therefore, you get s is equal to u times t, or s is equal to v times t, however you want to call it. So there you go. That's where that formula comes from. Right, so likewise, in section 2.2, there's that supposed formula that we don't have. W is equal to mg. All right, so again, holding that up to the camera. So weight is equal to mass times gravity. Boy, I really suck at making this thing focus. Okay, well, I think you guys know which formula that is, so I'm just going to put it back here. This formula comes from this top one here. Now, we haven't actually been introduced to any of these formulas yet, but it is coming from this top one, F equals ma. We are going to learn about this formula, actually all of these formulas, in the next video. So F is force. Now, in this formula specifically, it means net force, total force. Okay, so total force is mass times acceleration. When you're dealing with the force of gravity, which we represent as weight, which is capital W, what is the acceleration that the object experiences? It's the acceleration due to gravity, which we represent as lowercase g. And that takes on the value of 9.81 meters per second squared. Hence, this formula. So if you ever forget it, it comes from this, just as this formula comes from this. Okay? All right, so in case you forgot, because I've been talking a lot about the formula sheet, this is the problem that we need to do. Calculate the weight of a 25 kilogram object. So something simple to get us started. So example, we're looking for the weight. The mass of the object is 25 kilograms. All right, so required, given, and those ones you can put in any order you like. Analysis, weight is equal to m times g. All right, now let's solve it. So that's 25 kilograms, and g is 9.81 meters per second squared. All right, so, excuse me, 25 times 9.81, 245.25. Now, this is interesting because you know, because of what I've told you, that weight is measured in newtons. But looking at what's getting multiplied together, you have kilograms times meters per second squared, and somehow that's becoming a newton. And really, from what you learned way back in one of the first videos, we had our 7 standard international units, and the unit for length was meters, the unit for time was seconds, and the unit for mass was kilograms. And we said that there are derived units that are, well, comprised of these ones. And so in reality, what I want to show you is that 1 Newton is equal to 1 kilogram meter per second squared. So a kilogram meter per second squared is 1 Newton. We don't want to write kilogram meter per second squared all the time, so we just abbreviate it as capital N. Okay, something else I want to show you is that this value right here, the 9.81 meters per second squared, well, there's another way to write the units for that too. So this is a little bit on the side, both of these. Look at this formula for a moment. W is equal to mg. So if you were to rearrange that for g, you would get W divided by m. But what are the units for W? It's newtons. And what are the units for mass? It's kilograms. So newtons per kilogram. Now, if you wanted, you could substitute Newton with this whole thing, kilogram meter per second squared, stick that in the numerator, and then divide by kilograms, and you would be left with meters per second squared, which is exactly what you would expect for the unit of G. So you could do that. So 1 unit for G is meters per second squared, but another unit for G is newtons per kilogram. So if you ever see that G is equal to 9.81 newtons per kilogram, that is the same thing as saying it's 9.81 meters per second squared. It's the same thing. I just wanted to make sure that you all saw that. Okay, back to the slides. So we did this example. Now we figured out the magnitude. We have to figure out the direction as well. Actually, let me go back to the page here for a moment. So we have 245.25 newtons. With a lot of problems, it'll be easier to give a specific direction, but for this one, it's not exactly clear because, well, the problem is very general. So what we're going to do is we're just going to say down. Okay, down, or you can say towards the center of the earth. Either of those is fine. Excuse me. Okay, so back to the slides. Now, it does say here that note that weight inherits its direction from the fact that G points downwards, and that's true. Whenever we've calculated vector quantities, and one vector is equal to the product or quotient of something on the right side, and there's a vector on the right side, generally the direction of what's on the left comes from the direction of what's on the right. So because G points down, therefore W also points down. All right. Now I'm going to start introducing a new thing here, and that's free body diagram. A free body diagram is something that we're going to be using for the remainder of the course and also next year. It is so essential. And so because we use it all the time, we start abbreviating it as FBD. So if you ever see FBD, it's free body diagram. Now, usually with the free body diagram, you draw it as a point particle. So any object, no matter what it is. So this little dot could represent a piano, which is an abstract shape. It could represent a beach ball, which is almost a perfect sphere. Whatever it is, we represent it with a dot. And coming from that dot, we draw an arrow which is a force. In this case, the force is W. Obviously, we wouldn't label the dot mass and the arrow force. We would just put the dot with the arrow and then put the W to label which force it is. Since weight is going down, therefore we draw the arrow going down. In fact, this is a free body diagram of a projectile, an object whose only force acting on it is, well, the force of gravity if we ignore air resistance. Excuse me. Okay. Now, there are other forces other than weight, and there are many that you are actually familiar with. If you remember, in one of the very first videos we saw, there were 2 bighorn sheep on a slope, and they were pushing heads towards each other. And there were a lot of forces acting between their feet, between their heads, just in general acting on each goat or each sheep. Now, we looked at each of those forces, and I said we'd come back to them, and this is where we're going to come back to them. Imagine you have an object. Let's say you have a mug of coffee or a mug of tea sitting on your desk as you're learning about physics. There is a mass to that mug and the contents inside. So collectively, that mug of tea or coffee has a mass. So that force of gravity is pulling it towards the ground. Now, as it sits on your table, if your table couldn't support the weight of your mug, your mug would crash right through. And so imagine you had a piece of tissue paper just spread across 2 wooden rods. If you tried to put your mug of coffee on the tissue paper, it would rip right through because the structure of the tissue paper cannot provide sufficient upward force to balance the force of gravity. Your table is built very structurally strong, so it can provide that necessary upward force. Its structure is built with integrity. So when your mug is sitting on top of your desk, its weight is pulling it down, and the table applies an upward force to balance the weight. And that upward force is called the normal force. Now, a lot of people, when they first hear that it's called the normal force, they chuckle a little bit because it sounds like I'm saying it's an ordinary force. When I say normal force, I don't mean that it's an ordinary force. I mean that it's perpendicular. In mathematics, there are a couple ways of saying the word, or a couple ways of expressing that two things are at 90 degrees to each other. Well, we can say that they're at 90 degrees to each other. We can say that they're perpendicular. We can say that they're orthogonal. Okay, don't worry if you haven't never heard that word before. You will hear it when you study calculus in grade 12. And another way to say at 90 degrees is normal. So when two things are normal to each other, that means they're at 90 degrees to each other. So what is this force at 90 degrees to? It's at 90 degrees to the surface. Okay, so if you have, let's say, some kind of a box, if you drop it, its weight is what's going to pull it down towards the table. Actually, let me see if I can do that animation. Okay, never mind. I see the animation's not working. That's okay. If you were to drop it, the object would fall. Its weight would bring it down to the table. But the table then exerts a reactive force or a normal force going in the opposite direction. Now in your slides, the student version, as I know that this R is actually a capital N, and that's okay. I want you to become familiar with both because sometimes it's not just called the normal force, it's called the reactive force. So that's down here in the bottom in red. So either this force is designated with a capital R or a capital N. And so whichever one you see, you have to understand that these are the same types of forces. The reason why sometimes it's called a reaction force is because it literally doesn't exist unless there is an applied force, which in this case is the weight. So if you remove the box off the table, there's no more normal force. Another thing to keep in mind is that the table only exerts as much force as the weight pushes down on it. So however big this vector is, the reaction or normal vector will have the same magnitude, it just goes in the opposite direction. Notice that, actually hang on, let me just be careful with my wording there. The normal force does not necessarily go in the opposite direction of weight. It is just perpendicular to the surface. In this case, it happens to be to the opposite direction of weight. If your surface is on an incline, however, that's no longer the case, but we'll see those examples in time. So normal force, notice it's perpendicular, it's at 90 degrees to the surface of the table, and that's always going to be true. Last thing I'll talk about the normal force on this slide is that it's called a surface contact force. It only exists because you're in contact with the surface of the table, and that is why the arrow is drawn from the point of contact between the box and the table. So that's how we have to draw it. The weight, on the other hand, we draw it coming from the center of mass, which we approximate to be the middle of the box. Okay, so let's learn about some other forces. Tension. Okay, so tension would be you tie a rope onto an object and you're pulling on it. That's tension. Tension can only be a pull. You can't attach a rope onto an object, push the rope, and thereby push the object away from you. Tension only works as a pull. If you want to push, then you would have to work into something like a very taut spring, which we'll learn about in grade 12. Okay, so imagine we have a rope attached to the box. If we pull on that rope, all of a sudden now there's tension. The rope is taut, right? And because the tension is being applied to the point where the rope is attached to the box, that's where we draw the tension force coming out of, exactly where the rope is attached. And notice that it's pointing away from the box in the direction that is being pulled in. Now, as the box moves, or even technically if it's not moving, there's going to be a friction force here acting. Friction is a resistive force. So when two solid objects move across each other, there is a resistive force. So that's called friction. And it always, always goes in the opposite direction of motion, but it moves along the surface. So notice that friction, we draw this arrow coming from the middle of the box, but it is in the boundary between the table and the box. So where the two surfaces would come into contact. So each of these forces we draw where they're acting and in which direction they're acting. So again, force of friction is parallel to the contact surface. The normal force is perpendicular to the contact surface. Ergo, friction and normal are always perpendicular to each other. Always. That's always going to be the case. Okay. Friction is also called a surface contact force. If you do not touch a surface, you cannot have friction. Now, if some of you are wondering, well, what about when an airplane flies through the air or even a projectile? Even though we happen to be ignoring air resistance forces, there is still a resistance between the air particles and the object. Well, because the air particles are not what we consider to be solid, we don't call that friction, although it's still a type of resistance. We call that drag, and we will learn more about that towards the end of the video. Now, while so far all of these are contact forces, weight is not a contact force. It's what's called an action at a distance force. So what that means is an object does not have to be touching another object in order for it to experience a gravitational attraction or force of gravity towards that object. Okay, so think about any object. Imagine a ball, a tennis ball. If you throw a tennis ball in the air, excuse me, if you throw a tennis ball in the air, it will follow most likely a curved path, right, depending on how you throw it. So it will follow a curved path, and the only force acting on it is the force of gravity. Now, that's if you ignore air resistance. But throughout this entire time, the ball is never in contact with the earth. It's never touching the earth, but there's still weight acting on it. So whether you're touching the object or you're at a distance from it, you will always have that force of gravity or weight acting. Hence, it is called an action at a distance force. All these other forces, on the other hand, do require contact. Okay, so this is actually what I was just explaining earlier on an earlier slide. Weight is coming from the center of mass of the object. Normal or reactive force is always perpendicular to the contact surface. And, well, it's sometimes in the opposite direction of weight, but not always. Although the magnitude is usually equal to the magnitude of weight, as long as there are only two forces in the y direction. We have friction that's drawn between the surfaces, and tension is drawn from wherever the string or rope happens to be attached. Okay, so sometimes that's at an angle. All right, let's look at this. Oh, sorry, let me go back. An object has tension acting on it at 30 degrees as shown. Sketch in the forces and draw a free body diagram. All right, so let me go back to the page here. Excuse me. All right, so we've got our table, we've got our box, and we've got a tension force acting, and it's acting at 30 degrees above the horizontal. Okay. Now, this object has mass. That's guaranteed. So therefore, there's a weight to it. And we draw the weight coming from the center of the object going straight down. We label that as W. Because it's on a surface, there is a force from the table pushing back up on the box, just as the box is pushing down on the table with its weight. So that force going back up is called the normal force. It has the same length in this case. Well, okay, again, I got to be careful here. It's not the same length, but we'll draw a similar length to the weight. So we call that N, or you can label it as R. Now, if that box starts moving, well, there's going to be a frictional force as well. So F, friction. Now, if the box starts moving, we have something called dynamic friction, which, again, we'll learn all about the types of friction in the next section. So don't worry too much about writing this down. But even if the object is not moving, technically, there is friction there because you have some X component of force here. As we'll see, we're going to take tension and we're going to break it down into its components, X component and Y component. And if there is an X force, that means there has to be another X force in the opposite direction to balance it. So therefore, there can still be friction even if the object is not moving. Okay, let's go back. So here are our forces. Now, you see, even in the picture that I drew, in this picture, well, they're pretty much the same. notice that the forces are all coming out of different locations because this picture is really meant to show you where the forces are coming from. A free body diagram, you can either draw this diagram, this is actually better, but when you're actually calculating various quantities in these problems, it's going to be so much more helpful to draw all the arrows coming out of the same spot, something like this, right? So while this is not completely accurate, the one on the left is, I would say draw this picture first, right, representing the accurate free body diagram. Then when you start to do your calculations, you can always draw something like this afterwards. Just be familiar with both representations. Okay, now let's talk about something called resultant force. So we saw in an earlier video that resultant means total, it means sum. And another way to say that is net. So you have now 4 ways of saying total force, okay? So this is just the vector sum of all the forces acting on the object. All right, so let's look here. An object has a mass of 25 kilograms, a tension of 50 newtons, and a friction force of 30 newtons are acting on it as shown. What is the resultant force? Okay, so let's go back to our page. So we're gonna have to draw a new diagram here because we have a different type of tension. You know what, actually, I think I can fit it here. Let me go up. Example. All right, so we've got our table, we've got our box, so we've got tension acting to the right, we've got weight acting down, we've got normal acting up, and we've got friction between the surfaces going left. Okay, we need to find the resultant force. So because it's the sum of all the forces, I'm going to represent it like this. What is the sum of all the forces? Now, forces are vectors, and I have vectors acting in the y direction and the x direction. Because I'm dealing with x and y, I have to define my positive directions. So I always have to include this little picture here. So here's x, here's y, and these are the positive directions for x and y respectively. Now, in the y direction, there's only 2 forces acting. Now, you might say, okay, well, there's only 2 forces acting in the x direction too. But the difference is this box is getting moved to the right. It's at some later point in time, it's going to be over here, right? But at no point throughout its motion is this box going to be accelerating up and down, right? Or up or down. So I know that the normal force and the weight force are going to equally balance one another. N is equal to W. And so what that means is because they have the same magnitude and they're going in opposite directions, therefore the net force in the y direction is 0. And in reality, the net force, the sum of all the forces is coming from, excuse me, oh, really bad allergies, I apologize. The sum of all the forces in the x direction plus the sum of all the forces in the y direction. And if in the y direction everything is balanced, I can say that this is 0, which means I only have to inspect the forces in the x direction. In the x direction, I have tension and I have force of friction. So, but I have to keep in mind that there's different directions. Tension is going in the positive x direction, friction is going in the negative x direction. So when I calculate the sum of the forces in the x direction, this is going to equal tension, which is positive, minus force of friction, as it's in the negative direction. Now in the question I'm told that tension is 50 newtons and friction is 30 newtons. So 50 minus 30 is 20 newtons. So our net force is 20 newtons. Well, that's the magnitude. What direction is it going in? Well, because it's positive, I know that it's going to the right in our positive direction. So therefore we can say, let me write it down here, therefore the sum of all the forces, which just happens to be the forces in the x direction, is 20 newtons, and I'll say towards the right. Normally I would write right, but I'm a little bit running out of space there, so we'll just put the capital R. Excuse me. Okay, let's go back. Okay, so just as you saw in the previous problem, net force is sum of all the forces. So we can represent it as F net or sigma F. Either one of those means the same thing. And just as we have sum of all the forces in the x direction, we have F net x. We have sum of all the forces in the y direction, we have F net y. So it can be represented 2 different ways. Okay, next example. An object has exactly 2 forces, F1, which is 50 newtons, and F2 equals 30 newtons, applied simultaneously to it. What is the resultant force's magnitude? Something to keep in mind with this problem, this is not a true net force problem. And the reason I say that is we're not given the mass of this box. I know that in addition to this force, F1 and F2, there has to be a weight of this object because it is made up of at least one proton. I know that for sure. It's a box. So there has to be some weight to it, but I'm not given the mass, so I can't calculate the weight. So really, this example is not a real example. It's just there to show you how you would add F1 and F2 together. Okay, but it's not representative of a thorough problem. Okay. So let's go to our page. So we have our box, and we have two forces acting on it. We have F1, which is 50 newtons. So I think I mentioned this in an earlier video, but the fact that there's a decimal there, that's really for the IB students. It means that these two digits are both significant. So this is not one significant digit, it's two. And so we've got this, F2 is equal to 30 newtons. Okay, we have to find the resultant force's magnitude. So the resultant force's magnitude is a combination of the forces in the x direction plus all the forces in the y direction added together. In this problem, I only have one force going in the x direction and one force going in the y direction. And you know what? Just to be thorough and consistent, because I'm dealing with x and y directions, I'm going to define my positive x and y directions like so. Okay, so since I only have one force in the x direction, this is sigma f sub x, or you could just as equally call that f net x. Okay, and since I only have one force acting in the y direction, this is sigma fy, also known as f net y. All right, so some of the forces in the x direction is 50, some of the forces in the y is 30. But you know that this is a vector sum. I'm not going to do 50 plus 30 equals 80 newtons. That's incorrect. They are moving at 90 degrees to each other. When you add vectors, you add them tip to tail. So I would have one vector going to the right, and I would have one vector going up. So here's my 50 newtons, and here's my 30 newtons. And I know these are perpendicular since they're in the x and y directions respectively. Their sum, or the resultant vector, goes from the tail of the first vector to the tip of the final vector. So it looks like this. Now the way in which I find out this vector, I find out its length by using Pythagorean theorem, and I find out its direction by using inverse tangent. Now, this particular slide that we were on asks for the magnitude, but the next slide is going to ask us for the direction. So we're just going to do both at the same time here. So while this vector statement is true, I know that in order to actually calculate the magnitude of the hypotenuse squared, so that's this, is equal to the magnitude of the x component squared plus the magnitude of the y component squared. The reason I write it like this is so that it looks different from this line. This way I know that I'm dealing with magnitudes. All right, so therefore the sum of the forces is equal to the square root of sum of the forces in the x, which is 50 newtons, so that's squared, plus sum of the forces in the y, so that's 30 newtons squared. Okay, so 50 squared plus 30 squared, and square root that, we have 58.3 newtons. We just have to figure out the direction. That's pretty simple. For the direction, you're always going to use tangent because we know opposite and adjacent. I'm going to do that over here. So tan theta is equal to, I know it's going to be the magnitude of the sum of the forces in the y divided by the magnitude of the sum of the forces in the x. So theta is going to be equal to the inverse tangent of, so sum of the forces in the y, that's 30 newtons. Sum of the forces in the x, that's 50 newtons. So inverse tangent of 30 over 50, 30.96, we'll call that 31 degrees. Okay, so we have our magnitude, we have our direction. Of course, we don't want to just say it's at 31 degrees. We'll say it's 31 degrees above the horizontal. So therefore, the resultant force has a magnitude of 58.3 newtons at an angle of 31 degrees above the horizontal. Sorry guys, it's getting a little squished there, running out of space, but there we have it. Okay, so we found the magnitude and we found the direction. Let's go back. And of course, everything's in the slides. And this slide is looking for the direction, which we also found. Okay, now we have a similar scenario, except this time, instead of the forces already being mutually perpendicular, we have F2 in the same direction, but now F1 is going, well, on an angle. So let's see how we would solve this. Again, this is not a true example because we're not including things like weight, but nonetheless, let's go ahead and solve this. Okay, so example. So we've got our box. We've got F2, which is 30 newtons. And now we have an angle above the horizontal, which is F1, which is 50 newtons. And that's at 28 degrees above the horizontal. Okay, let me write that in a bit clearer. There we go, 28 degrees. Okay, so what I want to do is I want to once again define my positive x and y directions. So we have positive x to the right, positive y up. So like this. One of my forces already fits in with my direction system. That's F2. F2 is already in the y direction. Since F1 does not fit either the x or y direction, I have to break it down or resolve it into its x and y components. So I have to break it down into its perpendicular components. I'm going to take a different color here, and I'm going to break it down. So this is going to be here F1x, excuse me, and this one here is going to be F1y. So F1x is going to the right, and F1y is going up. Okay, and of course, F1x and F1y meet at 90 degrees. I really hope you guys can see that. I know the camera is going in and out of focus, but hopefully when it does go into focus, you can make out everything. Okay, now just like before, we are looking at the sum of the forces, right? This is what we're looking for. And I know that the sum of the forces comes from the sum of the forces in the x direction plus the sum of the forces in the y direction. But I acknowledge that x and y are in different directions, and so I have to add them tip to tail. The only difference between this problem and the previous one is that I can't just use the vectors I've been given, like in the previous question. I have to actually figure out what my sum of the x's and sum of the y is. So the sum of the forces in the x direction. Well, let's look at that. How many forces do we have going in the x direction? If you look at the picture, we only have one, F1x. By the way, now that you've taken F1 and you've broken it down into its components, forget about F1 now, okay? So now really what you're dealing with is three forces, F2, F1x, F1y. Okay, you only care about the forces that line up with your coordinate system. So how many forces do I have in the x direction? Just one, it's F1x. Okay, and F1x, it's going in the positive direction, so I can leave it as positive, right? Positive is going to the right. And it's the bottom of my right angle triangle. It's adjacent to the 28 degrees, so that's going to be equal to the hypotenuse times cosine of 28 degrees. Okay, so F1 is 50, so that's 50 times cosine of 28 degrees. Grab your calculator, 50 times cosine of 28. 44.1. All right, so 44.1 newtons is sum of f of x. Actually, let's put that in a circle because that's not our final answer. Sum of the forces in the y direction. So keep in mind that we defined upwards to be positive y, and in the y direction, looking at our picture, we have 1, 2 forces. Both of them are going in the positive y direction. They're both going up, so we can just add them together and keep them positive. So sum of the forces in the y is going to be equal to F2 plus F1y. All right, so F2, we can just use that directly. That's 30 newtons. I don't need to put the newtons here because I already know they're both in newtons. F1y, this one you're just going to have to calculate. It's opposite the 28 degrees, so it's going to be F1 times sine 28 degrees. So that's 30 plus 50 times sine 28 degrees. I think I can do that all in one step. 30 plus, in bracket, 50 times sine 28. That's 53.5. Another thing I should mention, make sure you're rounding properly. Okay, so I've seen in the past a lot of students will take this number or something like this, and they will round it as 53.4. You can't do that, because if you keep one decimal place, that means you have to look at the decimal that comes after it and see if you have to round it up or down. Since you have a 7, that goes up to a 5. If this is obvious to you, that's great. But if you are one of those people who would have written that as 53.4, please make sure you don't do that, because that would be incorrect. Okay, 53.5 newtons. This is going up, this is going right. So now we have sum of f of x, we have sum of f of y. Now we have to add f of x and f of y together, and we do that using our tip to tail method. So our x total force is going to the right, so that's 44.1. And our sum of the forces in the y is going up, that's 53.5. So sum of f of y, 53.5. And down here I have sum of f of x, 44.1. And I know that the resultant goes from the tail of the first vector to the tip of the final vector, like so. And these two meet at 90 degrees, and this is my angle. Okay, so as usual, I'm going to find the sum. So this is my sum. In fact, I don't even have to put the magnitude symbols around, because that's still a vector, it's an arrow. The magnitude of the sum of f is equal to the square root of the magnitude of the sum of f of x squared plus the magnitude of the sum of f of y squared. Okay, so that's going to be 44.1 squared plus 53.5 squared. So grabbing our calculators, 44.1 squared plus 53.5 squared, and square rooting that. So we have 69.3 newtons. Okay, so this is the magnitude of our resultant force. We have to find the direction, that's theta. So theta is going to be the inverse tangent of the magnitude of the sum of f of y over the magnitude of the sum of f of x. So that's the inverse tangent of 53.5 divided by 44.1. Inverse tangent, 53.5 over 44.1, 50.5 degrees. And that is above the positive x-axis, or above the horizontal. So we can say, therefore, the resultant force we'll just say is 69.3 newtons, and then square brackets we can say 50.5 degrees above the horizontal. If you want to be really specific here, you can say above the positive x-axis. Okay, so there we go. Going back to the slides. So again, remember that this is not a thorough, full question, and the reason for that is because we're not using gravity here. Really, the point of this example in the previous one was to show you how to add these two forces together. And if you notice, it's very similar to how we would have added displacements or velocity vectors, because they're still vectors after all. You treat them the same. Okay, so we did all this. Okay, next let's try this problem. An object of mass m is hanging via 3 cords as shown. Find the tension in each of the 3 cords in terms of m. So we have these angles relative to the horizontal, 30 and 45 degrees. We have a knot and we have a mass hanging. Something to keep in mind is that this system is not moving. That knot isn't moving and the mass m isn't moving. And this kind of question makes a lot of students uncomfortable. It shouldn't, but it does, because there are no numbers in the question, well, except for the angles. And even sometimes the angles aren't given. In this case, we're given angles, but we're not given the mass. So as we solve this problem, we're going to have to work in terms of letters. We're not always going to be able to solve everything in terms of a number. Okay, just give me 1 second, guys. Okay, so what I'm going to ask you to do, if you have your booklet in front of you, just grab a sheet of paper and draw that diagram onto your sheet of paper. So I'm going to do the same. I'm going to go over to my page here. Okay, so let's see here. We've got our ceiling, and we've got a knot. There's one rope attached here, and then it's at a bigger angle over here. And then we've got another rope coming down, and there's the mass. Okay, and this angle here is 45 degrees. This angle here is 30 degrees. By the way, you won't know this yet unless you've studied this, but 30 and 45 degrees as well as 60 degrees, those are what are called special angles. And in mathematics, you will learn about something called the special triangle. So most likely in grade 11 math, you're going to learn about it. It's very easy. Once you learn the triangle, you will inherently memorize the sine and cosine ratios for 30 and 45 degrees. Okay, so we are looking for the tensions in each of the chords. In order to find the tensions in each of the chords, well, they're different forces. So why don't we start off by labeling them? So I'm going to call this one over here T1. I'll call this T2, and we have down here T3. Now, how do I know that the tensions are not the same? Well, because they're different chords, they're different ropes. If it was the same rope, it would have the same tension, or at least this is how we would approximate it. But all of these are different ropes, right? And there's a knot in the middle, so there's different tensions. So T1, T2, and T3, and I'm not referring to the first 3 Terminator movies. I don't know how many of you guys are into that stuff, but anyways, really showing my age here. Okay, so we're looking for the tension. What I'm going to try to do here, there's a lot of stuff going on in this problem. I want to draw 2 sets of free body diagrams. I'm going to draw one free body diagram just for the mass, and I'm going to draw one free body diagram just for the knot. Okay, so actually, let me label that here. Knot. Okay, knot and mass. So I'm going to draw 2 free body diagrams, like I said. Okay, let's draw a free body diagram for the knot first. So knot FBD. Well, that's already given as a dot, so that's nice. So I have a tension force going like this, that's T2. I have a tension force going like this, that's T1. And I have another tension force going down like this, that's T3. Now keep in mind, the reason why there is tension in T3 is because there's a mass hanging on it. So whatever T3 happens to be, it's going to be as a result of the mass M, which we'll figure out when we draw the free body diagram for the mass. So what I like to do at this point, you should draw in some angles. So I'm going to draw my horizontal to the left, or sorry, to the right and to the left. Notice that this is 45 degrees here, right? So if that's 45 and this surface is, well, horizontal, this would also be horizontal. You get what's called the Zed pattern, right? So these 2 sides, the horizontal and the ceiling, they are parallel to each other. So you get this. Right? So these 2 sides are parallel. And if you cut it, you know that this angle and this angle are the same. Right? So that means that 45 degrees is also down here. I personally always like to draw my angles relative to the horizontal. It just, for me, it makes the calculation easier. If you want to do it based on the vertical, that's up to you. Just make sure you keep track of your sine and cosine ratios appropriately. So that means this is going to be 30 degrees. This one has a magnitude T2. This one has a magnitude T1. And of course, here I have my T3. Okay, so that's the knot. And now here, let's do the mass, FBD. This one I'm just going to label it as M. So because there's mass, there's going to be weight to it. So there is a W force coming down. And the only other thing touching it is rope T3. And so from the point of view of the mass, the tension is actually going up. Okay, so from the point of view of the knot, the tension's going down. From the point of view of the mass, the tension's going up. Okay, so they balance. Something else I want to point out, if some of you are looking at this and saying, well, hang on, the rope is made up of particles. There's mass to it. How come it doesn't have a weight? You would be right. Okay, for a lot of these examples, when we deal with ropes hanging things, we ignore the mass of the rope. So that's why we don't draw weight here for the rope. If we did, we would be given the weight of the rope in the question, but we're not given it, so we're not going to be using it. Okay, now I'm going to define my positive x and y directions as well. So positive x is to the right, positive y is up. You have to draw this every time, even if it's always going to look like this, which it won't, but even if it did, you have to include this. It is going to be for marks, for the live evaluations, and even for recording video tasks of yourself teaching the video how to solve these problems. Okay, so let's start off with the mass free body diagram. So in this case, I'm going to look at the sum of the forces in the y direction. And because this object is not moving, neither is the knot, but just because this object is not moving, I know that the sum of the forces in the y direction is 0. And so I'm going to say that 0 is equal to, now what are the forces? Well, I have tension 3 going up in the positive direction, and I have weight in the negative direction, so T3 minus W. And so really, I get a nice expression here. I get T3 is equal to W. Okay, now W is weight. Weight is equal to mass times gravity, and the mass here is represented by lowercase m, so that's kind of perfect. So T3 is equal to mg. And since we have to get our answer in terms of m, therefore this is okay, because remember g is just a constant. Okay, so now we have one less variable over here. Okay, so this gets plugged in over there. Now for the knot, we have forces going in the x direction and in the y direction. Because the knot is also not moving, it's not accelerating, it's still. That means the knot is in equilibrium. The forces in the x direction and in the y direction, they have to balance. Now, what I'm going to do on this picture, I'm going to break down T1 and T2 into their x and y components. So T2x is going to look like this. T2x and T2y is going to go up. And of course, those two are at 90 degrees. T1x is going left. And T1y is going up. And of course, those are also at 90 degrees to each other. Because I only have two forces in the x direction and they are oppositely directed, and I know the knot's not moving, these two have to be the same magnitude. They just have to. T1x has to equal T2x. All right. Now in the y direction, I have three forces. I have T1y, T2y, and T3. T1y and T2y are going up. T3 is going down. And so because the knot is not moving, these also have to be balanced. Imagine this is a tug of war. You have one really strong person down here and two not as strong people up here pulling. The efforts of their pulls has to equal the effort of this one person's pull. So T3 has to equal T1y plus T2y. And that's only because it's not moving, right? The knot's not moving. All right. So for the knot, let's do it in the x and in the y direction. So the sum of the forces in the x, keep in mind you defined right to be positive. So that means T2x is going to be in the positive and T1x is going to be in the negative. But again, I know that whole thing is equal to 0. All right, so because it's not accelerating. It's not moving. So 0 equals T2x minus T1x. So I can bring the minus T1x to the left side. So T1x equals T2x. Big piece of advice, whenever you have a force that's a component, always express it afterwards. So now I'm going to do it now. Always express it in terms of the original force and the angle. So either sine or cosine of the angle. So T1x is going to be T1 times cosine of 30 degrees. T2x is going to be T2 times cosine of 45 degrees. So at this point, I can just figure out what cosine of 30 and cosine of 45 is. Cosine of 30 is, let's take that to 3 decimal places, 0.866. So we have 0.866 T1, and cosine of 45 is 0.707. So you know what I'm going to do? I'm just going to isolate for T1 here. So that means I'm going to do 0.707 divided by 0.866. So T1 is equal to 0.816 T2. Oh, sorry guys. Let me scroll up here. Or let's scroll up. Let me move this up. Okay, so if you're looking at that and saying, well, okay, I simplified the expression, but I didn't really get any closer to the final answer. I mean, I don't have T1 in terms of M or T2 in terms of M. I have T1 in terms of T2, and that's not what I want. But this is a very important step in the problem-solving process. So I have T1 in terms of T2. I have two unknowns here after all, T1 and T2. But I'm going to make two sets of equations. In mathematics, you would have learned that if you have two unknowns, you need two equations to solve for them. You cannot solve for two unknowns given one equation. If you have three unknowns, you need three equations, four unknowns, four equations, etc. And I have two equations. One equation comes from the x direction, and one equation comes from the y direction. So sum of the forces in the y direction is also 0, okay? And that's going to be equal to, again, the positive ones, T1y plus T2y minus T3. Okay, so 0 equals T1y plus T2y minus T3. Well, T3 is just mg. Excuse me. Okay, so minus mg. Now, remember I said here, whenever you have a component of a force, always express it in terms of the original force. So T1y is T1 sine 30 degrees. T2y is T2 sine 45 degrees minus mg. So sine 30 is 0.5, so this becomes 0.5 T1, and sine 45 is 0.707, so plus 0.707 T2 minus, and well, you know what, at this point you can just call this minus 9.81, M, not G, because G is 9.81, minus 9.81 M. Okay. So at this point, let's bring the 9.81 M to the left, or the minus 9.81 M to the left, so it becomes positive 9.81 M, and that's equal to 0.5 T1 plus 0.707 T2. Notice now, if I call this here equation 1 and I call this here equation 2, I can substitute equation 1 into equation 2, and so I have two equations, two unknowns. I can solve for my missing variable. Okay, so I'm going to take T1 and plug it in over here. So I have 9.81 M is equal to 0.5 T1 plus 0.707 T2. Okay, so T1 is 0.816 T2. Okay, remember we want our answer in terms of M, so we're trying to get rid of the T2s eventually. What this expression is going to do is it's going to give us an expression for T2 in terms of M. All right, so let's do this. So it's 0.5 times 0.816. So we have next 9.81 M equals 0.408 T2 plus 0.707 T2. Imagine this was 4x plus 7x. You would get 11x. But I don't have 4 and 7. I have 0.408 and I have 0.707. So I add those together and I get 1.115. And I don't have x, I have T2. Okay, now I'm trying to get T2 on its own, so divide both sides by 1.15. That means I'm going to have 9.81 divided by 1.15 times m. Okay, 9.81 divided by answer. So T2 is equal to let's call that 8.8 m. Okay, that's good. So we have one of the tension forces in terms of m. Actually, we have T3 in terms of m as well, technically, because T3 is m times g, so T3 is just 9.81 times m. So all that's left for us to do is find the first tension force, and that is right here. So now that we have found T2, I can plug that back in over here and find T1. So T1 is equal to 0.816 times T2, which is 8.8 m. So 0.8816 times 8.8, 7.1808 m. Okay, 7.1808 m. Okay, and that's it, actually. You know what? To keep it to a low number of decimal places, I'm just going to call this 7.18 m. In fact, you could even call it 7.2 m if you wanted. But these are our final answers. So overall, let's just quickly review this because this was a long problem. Okay, if you need to watch it again, try the problem again, I would strongly encourage you to do that because that way it'll stick in your long-term memory. All problems that we're going to do have a very similar problem-solving strategy. Okay, so we have a knot and we have a mass. We're trying to find the three tensions. So since we have two stationary objects or points, we draw a free body diagram for each of them. The mass free body diagram, there's two vertical forces, weight and tension 3. The knot has three forces, T3, T1, and T2. So what I do is I take T1 and T2, given the angles to the horizontal, and I resolve them into their components, and I keep track of which direction they're in. Always define your positive direction. Since the mass only was dealing with forces in the y direction, I looked at the sum of the forces in the y direction, and I knew that they'd equaled 0 because this object is not moving anywhere. So I solved and got an expression for T3. Next, I looked at the knot. Since this is dealing with forces in the x and the y direction, I set up an expression for the x. Sum of the forces in the x is equal to 0, and sum of the forces in the y is equal to 0. Okay, so using each of these systems, I came up with expressions which I substituted into each other and ended up with T1, T2, and T3. So therefore, the tensions in the ropes are 7.18 m, 8.8 m, and 9.81 m. And then in brackets, you can say all in newtons, because it's going to look a little bit confusing and weird if, if we put mn. Okay. So there's that problem solved. Let's go back to the slides. Okay. So everything that we just did is on the slides. Okay. So here we have the same problem, except this time we're given the mass of the object. So the only difference here would be, well, if you look back at our question here, at our solution rather, we found T1, T2, and T3. If you're given the mass, which in this case we're told it's 25 kilograms, you just have to plug in 25 here, here, and here, and you'll find the exact numerical values of the tensions. Okay, so let's go back. Okay, so 25 times 10, 25 times 10. Give me one sec, guys. So that's 25. Sorry, they're using 10 instead of 9.81, so that's fine. T1, let's see here. T1, we had 7.18. Give me one sec here. Yeah, 7.18. If you take G, which is 9.81, and you divide by 1.366, you get 7.18, so 180 newtons, and 0.897 mg, so 0.897 times 9.81, 8.8, which is what we have. All right, you know what? We can actually just do this really fast on our side. If we know that the mass is 25 kilograms, let me do this in purple, so T3 would be 9.81 times 25, just to show you that the numbers are in fact the same. 9.81 times 25, 245.25 newtons. And T2, 8.8 times 25, that's 220 newtons. And finally, 7.18 times 25, 7.18 times 25, 179.5 newtons. Okay. If you're wondering why the numbers are a little bit different on the slides, it's because of sig figs, or significant figures, which is what the IB students will be paying attention to. Okay. This will be our last example for this video. A 1,000 kilogram airplane is flying at a constant velocity of 125 meters per second. Label and determine the value of the weight, W, the lift, L, the drag, D, and the thrust, F, if the drag is 25,000 newtons. Okay. This, you know what, I'm going to try to fit this on the bottom of an earlier page. So let's go back to our paper. I'm going to try to fit it here. Okay. You know what, I'll draw the airplane with the black marker first. Okay, so I'm going to do my best to draw this. So we've got something like this. Okay. Of course, you've got the wing coming out here and the wing coming out there. Okay. So we've got our airplane. We've got some forces acting on it. It has mass, therefore there is weight coming down. Now, the fact that the airplane doesn't fall out of the sky is because there's a lift force, and that lift force is going up. So, I mean, really the lift force is being applied here at the bottom, so we'll call that L. It's not a normal force, right? Because the airplane is not touching a surface. It's floating in the air or flying through the air. It's the air particles that are pushing up on the plane, which allows it to fly through the sky without disturbance. So we call that lift. Be careful not to call that the normal force. Thrust. The thrust is what allows the airplane to travel forward. So we call that F. And drag is the air resistance that the airplane feels, which pulls it back. Okay, so we call that capital D. Okay, so in total we have 4 forces acting on it. And we know that the drag force is 25,000 newtons. That's big, but I mean, it's an airplane, so you would expect a huge number. We're told in the question that the mass of the plane is 1,000 kilograms. Okay, this is a small passenger airplane. That's actually not massive at all. Flying at constant velocity of 125 meters per second. In fact, that is a very important piece of information in the question, that it is flying at constant velocity. As long as an object is not accelerating, if it is constant velocity or zero velocity, I know that the sum of the forces are going to be 0. Now, in this case, that is true for the y and for the x direction. Now, assuming this plane has reached its cruising altitude height, it's not going to have any acceleration in the y direction. So L and W are going to be balanced. And since it's traveling at constant velocity, its velocity being in this direction, these 2 forces also have to balance each other. Okay, let's go back to the slides because I realized we didn't even see what the question is. Oh, no, actually we did. Sorry. Determine the value of weight, lift, drag, and thrust. Okay, so weight, that's easy. Weight is equal to m times g. So our mass is 1,000 kilograms. G is 9.81. Remember, that's either meters per second squared or newtons per kilogram. Up to you. So 9.81. Now some of you can probably just do that in your heads. So notice that we get a number almost exactly like 9.81, just with the decimal moved 3 places to the right. So 9810. If you take any number and you multiply it by 1 with zeros after it, count how many zeros you have, and that's how many decimal places that your original decimal place will move to the right. Okay, so 9810 newtons. So that's our weight. Now, if the forces are balanced in the vertical direction, which they have to be unless this airplane is going up or down, it's not. So that means the lift has to equal the weight. So we'll say that since, excuse me, since the sum of the forces in the y direction is 0, therefore L equals to W, therefore L equals to 9810 newtons. Since I'm talking about x and y directions here, I have to define them. So I'm going to do that here. X, Y, these are my positive directions. All right, so we took care of L, we took care of W. D, we already know it's 25,000 newtons. So now we just have to find F. Since it's traveling at constant velocity, so since constant velocity, therefore, the sum of the forces in the x direction is 0. Therefore, we have F equals D. And notice that's the magnitude, okay? That's not the actual force itself. So if you want to get really specific, we can say it's the magnitude of the force, but don't be thrown off by that. So F is going to be 25,000 newtons. All right. Now, in reality, you know that the thrust force is going forward, the drag force is backward, lift is up, and weight is down. The reason we're not writing that here is because the question just says to determine the value of the forces, not the actual force itself. If it did, we would put directions with it as well. Okay, and so on the slides we have the same thing. They have decided to put the directions, but if it just says value, you don't have to put direction. But of course, not a bad way to put it either. So that is the end of video, well, 1 of 2 for 2.2 forces. Stay tuned for the next video, 2.2 forces, video 2 of 2.